The generalized circulation model is really a simple, idealized model of the world if it was a homogeneous planet. We don't have a homogeneous planet. We've got a planet that contains both land and water. And not only that, but when we talk about land, we've got topography. There's mountain ranges, there's valleys, there's canyons. And all of this different topography is absolutely going to affect the flow of air. It's going to affect pressure systems for reasons that we'll talk about later. It'll affect the flow of air, both with regards to the pressure gradient force and the Coriolis effect. However, if we assume a homogeneous planet, then we can create a globalized circulation model, which actually is going to be very beneficial for us to use as a study tool. So this is what I want to do. I want to draw the world like this. And then what we'll do is we'll put the equator here as well. And what I want to try to do is take this world and put on this world high pressure and low pressure cells, and then we'll take a look at the flow of air in an idealized fashion. Let's assume that the date is like an equinox, vernal, autumnal, it doesn't really matter. So let's put the sun here in the picture. All right, so here's the sun. Now as we take a look at the sun, where on the planet is receiving the most direct incoming solar radiation? Right along the equatorial zone. So in this picture, we certainly have heating along the equator. Now, if we have surface heating, what we're ultimately going to do is create a low pressure system, right? So imagine, for example, the sun is shining. It's shining down on the parking lot. The parking lot gets hot. The ground gets heated up. The air above the ground gets heated up. You'll recall from prior discussion, this warm air is going to expand and it's going to rise up into the sky. It is a low pressure system. So air that's flowing up is low pressure. Air that's flowing down is high pressure. So if we heat the equatorial region, we are essentially creating a low pressure system. So I'm going to draw a bunch of L's here. And the L's here are going to represent the equatorial low. So let me write that down. Equatorial low. I'm going to put some arrows here to represent that the air is flowing upward. Okay? Now, as opposed to the equatorial low, there's certainly going to be places on the planet which is going to be very, very cold. So where on the planet is it going to be really cold? Like freeze your balls off type cold. We're looking at the polar regions. Because at the polar regions, we're not receiving that much direct incoming solar radiation, not to mention the fact that if we're talking about summer or winter, we're looking at a 24-hour day or a 24-hour nighttime period. So we know that the polar regions are cold. And we also know that cold air can be heavy air. And heavy air is going to sink. And therefore, if it sinks, it's high pressure. So air that's flowing downward is high pressure air. So let me put some H's here. And we're going to call that the polar highs. So polar high. All right. Now you'll recall the last time we chatted about high and low pressure. I said there was a temperature component, and we see it right here. We've got warm air, which is low pressure. We've got cold air, which is high pressure, and that makes perfect sense. But I also told you that cold and warm air is not the key to high and low pressure. It may be here for the equatorial low and the polar high, but that is not the generic rule of thumb. And I'll show you why in just a second. In fact, I'm going to show you why right now. Because I like you. Let's go back to the equatorial low. We've got air pressure that's flowing upward, right? This air is not going to just leave planet Earth and go into space and be lost forever. The fact is the air is being held down to Earth by gravitational pull, right? So the air is flowing up. Gravity, however, is preventing the loss of this air. But here's the thing. We can't keep just pulling air up into the upper atmosphere. Air is dynamic. It's not static, which means it's got to move. So eventually, the air is going to get pushed toward the north and pushed toward the south, right? Eventually, however, the air is going to get pushed back down to the surface of the Earth. And by the way, the big question is, well, why is the air getting pushed back down to the surface of the Earth? That's something that we're actually going to chat about a little bit later on, in fact, today. And it's going to be called the conservation of mass flow. That's going to be the cause, well, conservation of angular momentum coupled with some mass flow. That's going to be the cause for this air being forced down. And we'll save that for just a second. There's actually a latitude with which this air is forced back down. And that latitude is right at around 30 degrees north and 30 degrees south latitude. And at this latitude, air is forced back down to the surface of the Earth. Now, if air is forced back down to the surface of the Earth, is that a high pressure or a low pressure? It's got to be high. Anytime air is going down, it's high pressure. So let me put a bunch of H's here. This is located at the subtropics, so we're going to call this the subtropical highs. So we've got the subtropical highs, the equatorial low, and the polar highs, right? Now, by the way, we had just said that the polar high is high pressure air because it's cold. You and I live at 32 degrees north latitude. You know that we're not a particularly cold latitude. So what do you suspect 30 degrees is? It's actually pretty hot, and it's dry. And most of the world's deserts are found at 30 degrees north and 30 degrees south latitude. So you see what I'm saying? This whole idea of temperature being the key to all the pressure differences around the planet is completely false. And we see that right here with 30 degrees north and 30 degrees south latitude, which is the subtropical high, and the subtropical high can be a pretty toasty location, right? Okay, so we're not done yet. We now have a surface high pressure zone at the subtropical high. We've got a surface low pressure zone at the equatorial low. We know that according to the pressure gradient force, air is going to flow from high pressure to low pressure. So if we take a look here at the subtropical high, we know that air is flowing from the high pressure to the low pressure. It's getting veered to the right of initial motion due to the Coriolis effect. So this is the flow of air between 0 and 30 degrees of north latitude. The same is going to be true in the southern hemisphere. Air is flowing from the subtropical high toward the equatorial low, and it's getting veered to the left of initial motion due to the Coriolis effect. We've just created some surface winds. These surface winds are going to be called the easterly trade winds. Easterly, because the wind is originating in the east and going to the west, trade winds. Anybody know why they're called the trade winds? You would think because they were trade routes, right? They were trade routes. But that's not why they were called the trade winds. Trade winds ultimately means fast-moving wind. And that's what we have, an easterly trade wind, fast-moving winds coming from the east going toward the west. So again, easterly trade winds, I'll just put ETW for easterly trade winds. Okay, so we got the subtropical high. The subtropical high is not due to temperature, it's due to a physical reason, the conservation of angular momentum, which we'll talk about in a second. We've got the equatorial low, which is due to temperature. We've got the polar high, which is also due to temperature. We've got the easterly trade winds, a fast-moving flow of air coming from the subtropical high to the equatorial low. Now, by the way, not to throw more nomenclature on you, but the equatorial low is not always known as the equatorial low. It's also known as a meteorological low, and it's known as the intertropical convergence zone, the ITCZ, which is actually a pretty good use of terminology. Intertropical convergence zone. And it's called the ITCZ because here you've got the convergence of the trade winds. And the reason why it's better to call it the ITCZ than the equatorial low is because it's not always found at the equator. This low pressure system is going to move with the seasons. In the summertime, everything's actually shifting northbound. In the wintertime, everything's shifting southbound. So we will call this the ITCZ instead of the equatorial low, and that's a much better term. Intertropical convergence zone. Okay, we're not done with our idealized model just yet. Because above 30, we got nothing going on right now when clearly there's got to be something going on above 30. And there is. Here's a high pressure zone, so air is flowing from the high and it's going northbound. It's getting veered to the right of initial motion due to the Coriolis effect. And here's air from the polar high. And it's doing the same thing. It's getting veered to the right of initial motion. So what we're going to note is that air from the subtropical high is going to converge with air coming from the polar high. And it's going to converge right at around 60 degrees north and 60 degrees south latitude. Now, once the air converges together, what do you think is going to happen to the air? It's converging together at the surface, then where's it going to go? Where do you think? It can't just stay there, it's got to move, because remember, we live on a dynamic planet of flow of air, not static. When the air comes together, when it converges together, there's nowhere for it to go but straight up. So the air will converge right at around 60 degrees north and south latitude, and when it does, the air will get forced back up into the atmosphere. If air is forced upward, is it low pressure or high pressure? It's got to be low. Anytime air goes up, it's low pressure, so let me put a bunch of L's here to represent low. We're running out of space on my diagram. We're going to call that low pressure zone the subpolar low, because we're beneath the polar regions, and now we've got another low pressure system. Now you'll notice too, we've got air which is flowing in the upper atmosphere. It's not going to reach out into space. Gravity will hold it down. So some of the air will flow toward the north, toward the polar high. Some of the air will flow backward toward the subtropical high pressure zone. And so this is going to be the grand generic picture. Wow, look at all that stuff. Now that subpolar low, is it due to temperature? If you've ever been to 60 degrees north or south latitude, you know it's not a particularly hot place to be. It's a little bit chilly. So that low pressure zone is clearly not due to hot temperatures. It also is due to physics. Air is colliding together, the air is being forced upward, and the upward flow of that air creates the low pressure system. Yes? Makes absolutely perfect sense, right? So now we've got the subtropical high and the subpolar low. Neither one of them has anything to do with temperature. It has everything to do with some form of physics. The equatorial low and the polar high, however, both have everything to do with temperature. Now, by the way, we're not done yet. Let me clear the board really quickly. This is getting a little bit messy. Let's draw this. And we've got our equatorial low. We've got our subtropical high. We've got our subpolar low. And we've got our polar high. And let's do the same thing down here in the southern hemisphere. Now we've got our easterly trade winds. But we also have wind flowing from here, from 30 to 60. And we're going to call that our westerly winds. And they're called the westerly winds because they're originating from the west and going to the east. So we've got our westerly winds down here. And then finally we've got our polar easterly winds. And they're called the polar easterly winds because they're originating from the poles and they're coming from the east and going to the west. It's pretty easy to name winds. Winds are just named from the direction from where they came from. So, easterly trade winds, westerly winds, polar easterlies. In fact, easterly trade wind, ETW. Right? The United States of America. What is the major wind that affects the United States of America? This is 30. This is 60. So clearly, US of A is right around here. So the westerly winds are the winds that affect us most. Now, of course, we've got Florida down here. So clearly trade winds affect those guys. But by and large, it's the westerly winds. And if you guys have started to watch the weather, which I'm sure you all have, I mean, if the choice is Honey Boo Boo or the weather, you're watching weather. And when you watch the weather and you see the satellite image, then you'll see this flow going across the United States coming from the west and going toward the east. And that's simply because our flow of air is really all predicated upon the westerly wind. It's the westerly winds which is really giving us our weather, right? But in addition to that, if they show Florida, for example, or even the eastern seaboard, then they're showing you winds that originate from the easterly trade wind route. And so the air is starting down here and it's moving upward. So we have these two major weather patterns affecting us. But in addition to that, as you watch the Weather Channel, they'll start to show you this low pressure zone here. And they'll start talking about cyclones and cyclonic systems. And then they'll show you like Seattle. And you'll see all this rain falling down there because of the low pressure system of the subpolar low. So we're starting to see why we have the weather that we do going across the United States, and this whole globalized circulation model really is a nice key to that picture. All right, let me give you some other bit of information. We know that this equatorial low is better to be called the ITCZ, and we'll talk much more about the ITCZ a little bit later on. The subtropical high is also known as the horse latitudes. So let me draw a horsey. I'm such a bad artist. And I want to say I'm a lover, not an artist. But I don't even know if I can claim that, to be perfectly honest with you. There we go, there's my horse. So 30 degrees north and south latitude, especially 30 degrees north, are called the horse latitudes. Anybody know why? The horse latitudes at 30 degrees north lat. The subtropical high is also known as the horse latitude. It has obviously something to do with horses. Now, I don't know if this is an urban myth or if this is reality, but this is what I've read. So you got to go back in the day. You know, shortly after 1492 when Christopher Columbus sailed the ocean blue. Shortly after that is really when North America was discovered. Not by Columbus, although yesterday was Columbus Day for reasons I'm not 100% sure. Our historical texts aren't particularly accurate when it comes to the discovery of the Americas, but that's all right. Let's just skip that. So we've got a handful of hundreds of years ago, the New World, and horses are being brought over to the New World, right? As horses are being brought over to the New World from the Old World, you've got these sailboats, and these sailboats are catching the easterly trade winds to get over here as quick as they possibly can. Well, it's not unheard of for boats to get stuck at the subtropical high. Winds at the subtropical high are weak. It's not like the easterly trade winds, which are ripping. Even the westerly winds can be pretty fast. Right here, you don't have much wind at all. It is a stagnant zone. The air is hot. The air is dry and the wind doesn't flow. So imagine that you're a sailboat and you are stuck at the subtropical high. Imagine that your cargo is a bunch of horses and you're stuck. Well, you could potentially eat them, but maybe there's a smarter thing to do with the horses. Why not rope the horses, tie them to the boat, throw them overboard, and hope that they just start swimming for their life? And they start swimming, and hopefully they pull the boat back into some winds like the easterly trade winds. Sail catches wind, then at that point you got to cut the horses loose so that the boat can sail away. So that's why I heard it's called the horse latitudes, because many horses were lost back in the day. And I'm sorry to say that. I know some of you ladies are probably really unhappy about that. You still have your pony and your unicorn posters up in your bedroom. I know some of you do. Come on now. My little niece, she's 6 years old. Her mom took her to horse riding the other day. Yeah? She wants to go horse riding. It's just this crazy fascination that young kids, especially young little girls, have with horses. And I hate telling this story to my niece, but I tell her every time I see her. I go, Nikita, remember why it's called the horse latitudes? Yeah, sweetheart. A bunch of horses were killed. I'm just kidding. All right. Everybody have any questions on the globalized circulation model? All right. Well, we've got one thing to address. And that one thing is, why is it that the 30 degrees north and south latitude is located where it is? So let's try to address that question right now. All right. There's something called the conservation of angular momentum. And it's a really cool physical concept. And you might not have heard about it before, but you actually know what it is. This is the conservation of angular momentum. Let's say that you're watching somebody ice skate. And they're doing the coolest thing. They start to spin. And when they spin, they throw their arms out. And when the ice skater throws his or her arm out, they start to slow down their spin. But then they pull the arms in, and maybe they do this action. And when they do this, they start to really rip it. I mean, they're spinning around fast. And I'm going to demonstrate this in a second. I've got a spin chair, which it kills me to do because I'm old now. I can't even go on a roller coaster that spins because I get way dizzy. You go to John's Incredible, they got that stupid ride inside there. My kids always want to go on it, and I'm going, oh, come on now. I can't do it anymore. I'm too old. It's crazy. But I'm going to demonstrate this to you in just a second. The question is, why is it that this skater is starting to spin fast compared to him initially when he was spinning slow? It's called the conservation of angular momentum. And this is what the conservation of angular momentum ultimately is. Momentum is your mass times your radius times your speed. Right? So we'll call this m times r times v. And because we've got the same guy in two different pictures, we'll call this r1 and this v1. Right? Now, when this guy pulls his arms in, two things are going to change with this person. His radius is smaller, right? Because radius was initially this, arm's length, but when he pulls his arms in, he's clearly getting smaller, and he starts to spin faster. M doesn't change, because dude is not picking up mass, nor is he losing mass. Conservation of angular momentum says the following, that whatever the momentum is before, it must equal the momentum after. Right? So M, R1, V1, that's angular momentum, equals angular momentum afterward. So this guy can pull his arm in, right? He can make himself smaller. But the fact of the matter is, mass can't change. So velocity has to. If this gets smaller, this has to get bigger in order for this equation to still hold true. Let's say, for sake of argument, that R2 equals 1/2 of R1. And we finish the equation. So M R1 V1 equals M 1/2 R1 V2. R1's cancel. We put 2 over here. So that means that 2V1 equals V2, meaning if this guy cuts his radius in half, he starts to spin twice as fast. Right? Does that make sense? That's the conservation of angular momentum. So when you watch the ice skaters do that, it's pretty kick-ass the way they can spin like that, because they just start ripping it. And I don't know how in the world they don't get dizzy, other than the fact because they practice it so much and they're turning their heads and they're trying to keep their eye at a singular point, that they don't get particularly dizzy. Oops. All right. You know, I could put this on here, but I don't want to fall and die. Okay, so I'm going to demonstrate conservation of angular momentum. In fact, I should probably have somebody, like one of you guys do it, but I'll do it. Yeah, really? Okay, so I'm just going to start spinning. See what I'm saying? So I just start spinning fast. All right, you're spinning. Hold on a second. So you know what happens when you get older? This is like, so a few weeks ago, I went to some friend's house, and I've never like shot tequila before. What the hell not? You know, I'm getting older. Might as well live a little bit. So he gives me a tequila shooter. I'm cool with that. Then he comes back later on. Here you go, Ken. Here's another one. Why not? I'm cool with that. Comes back a little bit later on with another one. Still feeling fine. Why not? Pop, pop, pop. Comes back a little bit later on. Okay. I'm still feeling good. Like, cool. You know, this is great. This is good tequila. I'm shooting it. All of a sudden, I get up. And the guy who's doing this with me, I know there's something wrong because we're having a barbecue, and he sends the 10-year-olds out to do the barbecue for us. And I'm going, oh, this isn't right. Now, I'm dizzy, but I'm still very lucid. I'm still in control. I just can't control. You know what I'm saying? So I'm not like going crazy or anything like that. Not like my friend who starts to... My friend comes up to me, oh, Ken, I love you, man. You remind me of my brother. I love you. I'm going, oh, come on. Really? So I go out, and I see the two boys just absolutely hockey-pucking the hamburgers. Hockey-pucking them. And I'm going to this one kid, listen, that burger's done. I'm drunk, but I know that that burger is done. And then I'm talking to my son, and I felt so bad. I'm so embarrassed to do this in front of my kids. So I go, Sebastian, I got to go inside now because I'm about to be sick. And I'm very lucid with this. Go to the bathroom, do what I got to do, get up, the world is spinning. And the scariest thing is I can't control that spin. It was the worst feeling in my life. Yes, and this was like 3 weeks ago. Yesterday, go to Miguel's, get a margarita, you know, on the rocks. Can't drink it. I take one sip and it's just flashbacks. I can't drink it. I can't do it. But the spin I just had was the spin that I had, but this spin went away, and that spin carried with me for at least 36 hours. I know. Can't do it anymore. Anyway, I'm sorry, I digress. You got to be asking yourself now, how does this have anything to do with the flow of air at 30 degrees north and south latitude? Ice skating and whatnot. Let me show you. All right, so let's go to the ITCZ. And we know that we've got a low pressure system here. And we know we've got this mass of air, and the mass of air is flowing this way and it's this way, so it breaks into two essentially. Now, you'll know that this mass of air is going to have a certain mass, and we'll call that M. Right? We also know that the mass of air is a certain distance away from the center of the planet. We'll just call that R. And we also know that the air is actually flowing around the planet, i.e. the jet stream, and it's flowing around at a velocity of v. So it has an angular momentum. But here's the catch. As this air is flowing northbound and southbound, guess what's happening? The R used to be bigger. The R is now getting smaller. You know that the circumference of the Earth, i.e. the diameter and the radius of the Earth, gets smaller as you get to higher latitudes because we live on a sphere. So if R goes down, then velocity obviously has to increase, and so the air starts to flow around the planet faster and faster and faster. It reaches a point where it just simply cannot flow any faster. So the conservation of angular momentum has been maximized. And the only way for nature to correct itself is for the air to drop. Because once the air drops, surface friction starts to slow the air down, but more importantly, mass starts to be lost. Because now we can start removing mass with the easterly trade winds. And then, of course, we start the process all over again where we get to the ITCZ, the air flows up, it heads toward the subtropical high, and it goes down again with the easterly trade winds, and we have this constant movement and circulation of air. But that conservation of mass flow really becomes the key to the subtropical highs. Does that make sense? All right. Let me give you one more bit of information. Let's draw this picture. So we've got air flowing from the intertropical convergence zone to the subtropical high. And it flows back to the ITCZ with the easterly trade winds. We call that Hadley cell circulation. And it's called Hadley cell circulation after a dude named Hadley, because he came up with it. We also have right here Ferrel cell circulation. So here's our subpolar low. And we would call this circulation pattern Ferrel cell, named after the dude who came up with it. Now again, this is a simple globalized circulation model. It's idealized, right? It only really works with a homogeneous planet, which we don't have. With that said, let me ask you the following question. In which hemisphere do you think this model is better predicted? That is, where does it work better, the northern hemisphere or the southern hemisphere?
Southern.
If you say southern, why?
Because there's less population.
Not, yeah, it's not population.
Landmass?
Landmass, right on. There's less landmass. So when we take a look at the southern hemisphere, it's closer to homogeneity than the northern hemisphere is. There's more land up here. So the southern hemisphere, we find that this globalized or idealized circulation model is a little bit more realistic. But with that said, when we start talking about different wind patterns across the planet, this whole idea is going to be pretty good. It's pretty decent. Okay, does anybody have any questions on this at all? All right, now, you're going to hate me for this, but let me show you an animation. You're going, animation? You just spent 20, 30 minutes talking about this, and you could have shown me an animation from the beginning. It's important that we derive this picture, because when you derive the picture, you're going to understand it a little bit better. Keep in mind, we looked at pressure system, we looked at pressure gradient force, we looked at all the tools we need to figure out this globalized circulation model, so that's why I derive it instead of just showing you the animation. But let's go to that right now.